Hello, welcome back. This is the last portion of Unit 1. This is 1.11, although it's a little bit of a combination of what would have been in 1.10 as well. I just sort of made this slightly smaller, so we're going to talk about feedback loops, the laws of thermodynamics, and just sort of summarize energy as a concept as well. Our learning objectives for today are to discuss the first and second laws of thermodynamics and explain how they influence environmental systems. So really we're going to be applying those to trophic pyramids and trophic levels. We're going to explain how scientists keep track of energy and matter inputs and outputs and changes to environmental systems. And we're also going to differentiate between positive and negative feedback loops and look at how we can also apply those to environmental systems. So first, just to look at energy. Sorry, this is a plain slide. We know that energy is a vital component to any system, specifically to any living system. So all of our systems on this planet, all of our organisms, nothing survives without energy. And of course, we know that all living systems absorb energy from their surroundings. And depending on the type of system we're talking about, that energy can come from different places. So for instance, if we are an animal, or a human, anything, animals absorb the energy they need for cellular respiration from food. So we have to consume something that contains energy, and that then becomes energy for us. Additionally, we know plants get their energy from the sun through the process of photosynthesis. They make sugars, and then those are the sugars we then consume. So energy is constantly being moved around, and this is going to bring us right into the topic of the first and second laws of thermodynamics, but it's important to note we have the same quantity of energy always. It just keeps getting moved through different systems, through different entities, and it changes its form. We also have things like constructed human systems that also utilize energy. So for instance, gasoline can be a form of energy, can be a form of kinetic energy or chemical energy. We can convert that gasoline into the kinetic motion of that car moving by breaking chemical bonds, which is a form of chemical energy. So all these different systems, whether they be living or non-living systems or constructed systems, all require some form of energy, and that energy just keeps getting moved around. So I sort of mentioned these already, but these are the types of energy we'll talk about in this class. So there's potential energy. This is stored energy that hasn't been released. A really good example of this is Hoover Dam, or a dam in general. This happens to be a picture of Hoover Dam, but the dam wall itself holding back all of the water that's sitting in the reservoir behind it, that is potential energy. If the dam wall were to be removed, all of that water would flow, and it would be flowing in the form of kinetic energy. But the ability of that water, or that water sitting behind that wall just ready to be moving, that's potential energy. We've got chemical energy. This is energy stored in bonds. This is what we see when we look at cellular respiration. As we break down that energy that we've consumed into like usable sugars for us, that's a type of chemical energy in the form of cellular respiration. And then we also have kinetic energy. This is the energy of motion. Once the dam releases, if we were to remove the wall, all of that water would be flowing, and that would be an example of kinetic energy. And then temperature is also a type of energy. It's just the measure of the average kinetic energy of a substance. So it's heat energy. In fact, a lot of energy is in the form of heat. Okay. So let's take a look at the laws of thermodynamics. I've mentioned the word system a couple times in this video already, but it's important to know that when we're talking about energy flows and we're trying to decide how the first and second laws of thermodynamics are applied, we're always talking about the system, not necessarily the surroundings. So let me give you an example. If I'm talking about the kinetic energy or the temperature of boiling water on a stove, and I'm watching that temperature shift from a liquid state to its gaseous state as that water continues to heat up, the system that I'm evaluating and the type of energy flow that I'm evaluating is the water, the pot, and maybe the stove. That's the system. The surroundings are maybe everything else in that kitchen, the microwave, the kitchen counter, the table, whatever it is. Those are the surroundings. So generally when we're talking about the laws of thermodynamics and we're talking about energy flow, we're talking about it specific to the system, because there's so much energy flow with everything around us. We have to really narrow it down and be specific to what we're talking about. So we're talking about the system. Now, the first and second laws of thermodynamics really shouldn't be new to you. The first law of thermodynamics, and we're going to break these down even further, is a physical law which states that energy can neither be created nor destroyed, but can change from one form to the other. So we'll expand on that. And the second law says, and these are written kind of in fancy terms, but the second law is a play on the first law. It's basically a continuation. It says that when that energy is transformed from one form to another, the quantity of energy remains the same, but its ability to do work diminishes, so it no longer becomes a usable energy. So if you're confused, that's okay. Let's break them down. So the first law of thermodynamics, let's just say that all the energy in the universe, so all of this, everything that's in the surroundings, that never changes. We have the same quantity of energy always. It's just constantly moving to different forms. So we can never destroy that energy. We can never create more energy. It is a constant type of energy. And so, again, the example here, so plants convert the energy of sunlight into chemical energy, into stored molecules. Living things can then eat those stored molecules. That energy then moves from the plants into the animal that consumed that plant, etc. The animal that consumed that energy will then release that energy again in the form of cellular respiration as they start to move. If they're walking, riding a bike, hunting, whatever it is, that energy then moves to something else. And so that's what the first law basically says, that we're not creating any new energy, it's just constantly moving to different sources. What is important to note is that as those transfers occur, they're not completely efficient. So let's say I have 100% energy in my plant and I have a consumer come in and eat that plant. I don't get all of that energy back into me as the consumer. What I get is I get a small amount of energy, and then I lose some of it to heat energy. That is the start of the second law of thermodynamics. So let's take a look at that. Oh, here's a little bit more on the first law. This is a human-made system. So our energy input in the form of chemical energy or potential energy is gasoline, and then as we combust that gasoline, our energy output is not only that the car is able to move, but we also get heat energy as a byproduct. Most of that heat energy is then wasted. This is kind of what we're talking about, that not all of that energy transfer is completely efficient. Sometimes it's released and is no longer in a usable form. So we have this energy transfer from the gasoline into the car, but the car isn't using it fully. So instead, we get some of that energy used, and then some of it is lost as waste energy. And that's what the second law of thermodynamics is, that it can change from being useful to not useful. And usually that non-useful energy takes on the form of heat. This is exactly what we're seeing happen between trophic levels and what the rule of 10 or 10% rule sort of implies. The rule of 10s, as a reminder, basically says, or the 10% rule basically says that only 10% of energy becomes useful to each trophic level as we move up that trophic pyramid, because a lot of it is lost during cellular respiration in the form of heat. So for instance, in this silly image, we've got this person eating like a hot dog or something, and they're consuming the energy in the form of hot dogs in order to help them move, to give their body energy, and some of that energy will be used to make their body move, but a lot of it will be lost in the form of heat as your cells are respiring as they break down those complex macromolecules. Okay, and also you're losing some as carbon dioxide and water, of course, but all this is saying is that you're not fully using all of the energy you consumed in an efficient way. And that's what we see in trophic levels, right? As we move through those trophic levels, less and less energy becomes available because we're losing such a significant amount to cellular respiration at each of those levels. Because that heat that gets lost from each in this case, because of that heat that gets lost from the person or through cellular respiration through each of those trophic levels is no longer doing work, we call that moving towards randomness or disorder. The official term for it would be moving towards entropy. So entropy just means that if energy has the ability or wants to always move towards disorder. So unless we apply more energy to it, energy will always move towards entropy. And that means it will always want to move towards randomness or towards chaos. So let me give you sort of an overview example that has nothing to do with maybe science. But let's say on Sunday night, before the school week starts, you clean your room. You make your bed, you put your books away, all your laundry's put away, your room is completely reset. As the week continues, you may get tired, you may get busy, your room is going to start to get messy, your bed's not going to be made, you're going to have laundry all over the place, your textbooks are going to be out because you're going to be studying. And that you're not putting in, you're maybe tired, you've got other things going on, you're not putting energy into keeping that room clean. So as a result, your room is moving toward constant disorder or randomness. It is moving towards entropy. If you apply energy to your room and you get it back to normal and you keep it clean, then that becomes a usable form of energy again. So another example. So in this case, we're looking at, this is supposed to be a coal burning power plant. When we burn coal, even though coal is an energy source, only about 35% of that coal, and this is an approximation of course, only about 35% of that coal is actually goes into making energy that transfers through our grid system. 65% of the coal burning process is lost to heat. This is that entropy we're talking about. This is energy. Heat is a form of energy, but it's no longer usable energy. So that 35% goes toward our power grid. Even as that energy or electricity is transferring through our power grid, 10% is lost again as heat energy. And then once it gets to our house, if we're using an incandescent bulb, which are those bulbs that get really hot, 95% of that energy gets lost as heat and only 5% goes toward actually making the light. So if we're using coal and incandescent bulbs to make electricity, we're really only 1.6% efficient. And that is what the second law of thermodynamics says. Even though we started with all of that energy, not all of it becomes useful, and most of it is moving towards entropy in the form of heat. Okay, a little bit more on defining systems. So systems, again, I showed you this image, how we define a system. It's a system and its surroundings. We can further break that down. So systems can be defined as open and closed. So an open system is going to be a system that has an exchange of matter and energy across boundaries. So for instance, this tree, if I say this tree is the system, it's going to be an open system because I'm going to see an exchange of inputs and outputs happening across the system boundaries with its surroundings. So for instance, this shows you what those inputs and outputs are. The inputs are going to be heat and light and nutrients and water. All of that is going to go into supporting the tree, and the tree is going to give off oxygen, it's going to give off water, it's going to give tissue to other trophic levels, it's going to give decomposition to soil. Those are the outputs. So in an open system, we see this exchange of matter in and out, in and out, in and out. Whereas a closed system is going to be something that does not have an exchange of matter. Energy exchange will occur, but we don't see this exchange of matter. And I'll give you an example. Our planet is actually considered a closed system because the only input to our planet is energy. It's sunlight. There's no other inputs that are contributing to our planet. Nothing from outer space comes onto our planet and adds matter to our planet. So planet Earth is actually considered a closed system, and then within Earth, all of these ecosystems are considered open systems. And we look at that matter and energy transfer as either inputs or outputs to the system. When our inputs are equal to our outputs, that's called a steady state. Our steady state, meaning our ecosystem is at an equilibrium, that's when our inputs are equal to our outputs. Okay, so that's on system and energy movement through systems, and this is our last big idea. It's going to be on feedback loops. Feedback loops are another way that we can evaluate energy and matter movement through an ecosystem. So a feedback loop is the part of a system in which some portion or all of the system's output is used as an input for future operations. So just like the title suggests, these are going to be loops. And they're a little bit of a misnomer because a negative feedback loop sounds like it would be a bad thing, and a positive feedback loop sounds like it would be a good thing, but it's really the opposite. A negative feedback loop is going to be change that allows us to return back to our original state or status, Whereas a positive feedback loop is change that will lead to more change. We're just going to keep changing. So we'll never get back to our original status. So let me show you some examples of this. So a negative feedback loop. I'll do this one in a minute, but let me give you an example. So let's say you want to go for a run and you're running a mile. You start running. What's going to happen to you? You're going to start sweating. Your heart rate is going to go up. Your breathing is going to become more labored. Your body temperature will start to increase. All of these things are moving you away from your body's homeostasis. So all of these changes are going to add. As soon as you stop running, your heart rate will decrease, your body temperature will decrease, you'll stop sweating, etc., and you will return back to the original status of your system, right? You will return back to your regular resting heartbeat, your regular body temperature, etc. That's a negative feedback loop. So we have all these changes that have occurred to the system, temperature, heart rate, etc., but all of those changes eventually lead us back to us being back to our original homeostasis. Okay, so in this example of a negative feedback loop, we have a closed canopy in a rainforest. This means that the trees are so dense. This is something we'd see in like a tropical rainforest. The trees are so dense in the top layer that no sunlight is actually able to penetrate through. So the floor of the rainforest is actually going to be very dark because the trees are going to be so dense they're going to create almost a canopy-like structure over the top of the rainforest floor. If wind blows down old trees, what happens is light will start to enter that forest floor again. This is good because we know that new growth requires sunlight. So this now allows a young tree to grow because they don't have to compete for light. And there's a source of light coming directly down in this opening in the canopy, and that young tree will then be able to grow and replace the old tree and replace the really strong full canopy that is the top of the rainforest. So again, we have all these changes. We're seeing a loss of trees. We're seeing an increase in light. We're seeing new growth in trees. But we're eventually getting back to our original status. Now, a positive feedback loop, by comparison, is usually change that doesn't get us back to our original status. So in this case, we're starting with an increase in temperatures. So increase in global temperatures. As those global temperatures increase, we see ice or permafrost thaw that hasn't been thawed in a really long time. As that permafrost continues to thaw, we release more carbon dioxide and methane, which are greenhouse gases, which will contribute to increasing the global temperature, which will contribute to more permafrost thawing, which will contribute to more carbon dioxide and methane being released, and more temperature, and on and on and on. And we never get back to an original status. We just continue to amplify the change that is occurring within the system. So global climate change is a really good example here. Okay, that's all I have for you guys. Let's check back in class, and I will see you soon. Thanks.